Now I'm going to move on to serial communication interfaces that are used typically on microcontrollers to talk to other instrumentation, usually smart instruments that are attached to them. And the first one I'll mention is the serial peripheral interface bus. The idea is you start with an SPI master. That's usually the main microcontroller in the system. And then you have a bunch of subordinate elements slave to that master controller. So this might be a pressure transducer and a temperature transducer and a rotation rate sensor. And each of these communicate back and forth on their own serial lines. So they've got a common clock. The clock goes out to all of the different ones, so they're synchronous. They've got common data transfer paths, so that those are used by all of the different pieces that are attached. But they've got separate chip select pins, so we can control which device is supposed to talk. And the master is going to tell which slave device to talk or listen at any particular time. So it needs 4 wires for a single connection, in addition to ground, and it provides full duplex with clock and one transmission line in each direction. So it can be pretty fast. The downside of that is additional slave devices require individual select lines. But you can get speeds of more than 10 million bits per second. That would be 10 million baud. So that's about 100 times faster than a serial connection. However, it's often slower depending on what the interface devices are. This is a common way for interfacing with SD cards, for example, to save data, or displays using the Arduino SPI library. Now, I2C, the inter-integrated circuit protocol, was devised to allow multiple integrated circuits, usually on the same circuit board, to talk to each other. It has only 2 wires, SCL and SDA. They're digitally modulated, so alternating up and down, and they're bidirectional. That means that the data can only go in one direction at a time. We call that half duplex. There's 7-bit addresses allow the master, usually a microcontroller, to communicate with multiple sensors on the same wires. But what that means is that these addresses have to be sent up and down those data wires instead of having a separate chip select pin. We have fewer wires to connect, but it's going to go slower. About 1/3 the speed maximum of the SPI bus. But this I2C is a very common protocol for connecting sensors to microcontrollers, and it's the one we're going to use in this lab. The Arduino wire library, it's called Wire, allows you to use I2C, and the library is really similar to the serial library. Wire begin starts up a connection. Wire begin transmission to an address sends something off to the address. You can write and read and then end the transmission. So we can get more data back and forth to our sensors, and one of the big advantages there is that sensors can store their own calibration information. That means you can have a factory calibration of a sensor, and it can save those parameters right on the sensor chip, so that the first thing you do when you call up the sensors, you say, and what are your calibration parameters? What should I use to convert the data you're sending back to me into the correct values? And it also means that the sensor can have different operating modes, because if I can communicate multiple different things back and forth to the sensor, I can tell it how I'd like it to be operating at this particular time. And one sensor can send back multiple measurements. For example, the BMP sensor provides pressure and temperature, both from the same instrument. And the newer BME280 provides temperature, pressure, and relative humidity, all from the same instrument. And the BMP180 is the sensor we're going to be using this week and also later on in the course in MEC 217. So here's what the BMP180 looks like. It's a sensor from Bosch. It's not very big. That tiny little chip there is the BMP180. And it provides pressure measurements in mostly the atmospheric pressure range, from about 1/3 of a standard atmosphere up to a little over 1 standard atmosphere, so that you can go from about 9,000 meters up, i.e. above the top of Everest, down to minus 500 meters below sea level in the Earth's atmosphere, and still get a good pressure reading. It has really low power consumption, 5 microamps power consumption if it's operating at 1 sample per second. So this is the perfect thing to put in your phone if you want to know what the pressure is. And it's about $2 a unit. So these are really nice devices. They do really useful things. And the temperature measurements included. It has an I2C interface to communicate back to your microcontroller, and it supersedes the similar but older BMP180. However, this chip, even though we're still using it now, it's been superseded more recently by the BMP280, and that BMP280 has both I2C and SPI communications, and that's probably what you'll find in your phone if you've got a fairly new phone, a 2016 or later vintage phone. Power consumption. Let's just put this power consumption in perspective. If a BMP180 is using 5 microamps average current in low power mode with a 3.3 volt supply, then the power it's consuming is voltage times current, gives me 16.5 microwatts. Now let's compare that to, say we made a Wheatstone bridge of 100 ohm sensors, and we put those strain gauges together and supplied them a 3.3 volts excitation voltage for the bridge. The current is voltage over resistance, so we're going to have about 33 milliamps drawn by that bridge. The power will be the voltage times the current. That'll give us about 1/10 of a watt. So quarter watt resistors are still okay in here. That's not very much power. However, it's a lot more power than this 16.5 microwatts. There's a difference of 10 to the 5th there in the magnitude of power consumption. So if we took 2 AA batteries, which are good for about 2,000 milliamp hours, we'll get that to last about 61 hours just powering the bridge. So to power our strain gauge bridge and not do anything else, not run a microcontroller or anything, we will still only get about 61 hours out of our batteries. On the other hand, all other things being equal, there's enough power in there to power that BMP180 for 45 years. So that BMP180 represents a really tiny part of the power consumption that goes on in your phone. Now, if we want to use a BMP180, the first thing we've got to do is go out and ask it what its calibration coefficients are. And if we look in the library code that you're going to have a look at later, that's exactly what it's doing right away. Is it's going out and reading 16-bit values from the actual sensor to tell it what the calibration coefficients are. You only need to read this once when you hook up to the sensor. It's not going to change. It was set at the factory, and that's the way it's going to stay. Then you read the raw data and correct it mathematically by those calibration coefficients. So you write a request out to the sensor at its address. That's what's happening here. Then you wait a little while. That's what's happening here. It's delaying for 5 milliseconds. And you know how we hate this delay call here. and then it's reading a 16-bit value back in from the sensor. Then it's got to go and convert that information into an actual result. So this is an example of how it does the conversion for the temperature. It reads the raw temperature data. That's this function up here that it's just got this data from. And then it calculates a B5 value from the raw data value, and then it adjusts the temperature to get an actual temperature in degrees Celsius. And there are similar conversions going on for pressure in hectopascals or millibars or pascals. Now, you may have seen some funny C operations there. This one, for example, A and 2 arrows pointing to the right. By 3, that means shift the bits in variable A by 3 positions to the right. The least significant bits fall off, and it's equivalent to dividing by 8, but it's potentially somewhat faster. So 107 in binary would look like this in zeros and ones, and if we shifted it to the right, then we'd go 1 over to the right, 0, 0, 1, 1, 0, 1, 0, 1. This 1 fell off, and we get 53. Shifted right again, we'd get 26. Shifted right again, we'd get 13. So each shift to the right is dividing by 8, or sorry, each shift to the right is dividing by 2 and rounding down. And yeah, that's about 1/8 of 107, allowing for the round off of dropping these bits. And each shift to the left, that's 2 arrows pointing in the opposite direction over towards the left, is multiplying by 2. And also, you should note that B plus equals 5 is the same as B equals B plus 5, but more compact. So those are just a few things you might notice as you're looking over some of the source code. Now, because this is a chip that's got multiple operating modes, you've got to decide how you want to sample the pressure. That's one of the pluses of digital communication, is it allows that configuration of the sensor from the microcontroller so that the sensor can do some of the work on its own. Now, in the BMP180, it will either take 1 sample and send you the data right back, or it can take up to 8 samples and internally sum them up and average them and send back the average of 8 data. And we know that the noise is reduced by the square root of n when you average, so we can get a better measurement of the pressure without needing to do any more work on the microcontroller. We don't have to gather all 8 of those samples. We just need to tell the sensor to go and get them, average them, and send them back to us. The time it takes to take each number of samples varies by the number of samples being taken. So, for example, if you look in the code, here it's looking at what is the oversampling. If it's in ultra low power mode, that's take only 1. It only needs to delay for 5 microseconds to wait for it to convert the samples. However, if it's taking 8 of them, it's going to have to wait a long time, 26 milliseconds. And we hate waiting that long, especially with that delay function. So that might be something we'd like to address. And that's actually a problem that's been solved on the BMP280. So those are the processes that the library will go through on our behalf to get some digital data in from that BMP sensor. And it saves us a whole lot of messing around with analog to digital conversion and a whole lot of problems that would be associated with noise. Now, there are a wide variety of other protocols for communicating wirelessly. One of them is the CAN bus. A controller area network is a specifically vehicle-based standard, and it's designed to go into cars, trucks, any kind of vehicle, and allow multiple microcontrollers to talk to each other and talk to their sensors by sending messages back and forth. So CAN bus is one of the 5 protocols used in the official OBD2 vehicle diagnostic standard. And that OBD2 has been mandatory on all cars since 1996 in North America, and since 2001 in the European Union. So it's a really widely used communication standard. Now, we're not going to talk about it any more than we do now, but I will note that there are multiple microcontrollers, not including the Arduino Uno, unfortunately, that support this CAN bus networking. And so if you want to build something that's going to go onto a vehicle, you'd better make sure that you've got a CAN bus compatible microcontroller. CAN bus still needs wires, and that's usually not a problem on a vehicle. But what about if we want 0 wires?